It's okay. Okay, thanks Ian for the introduction. And so good afternoon to everybody. So I'd like to join the other speakers in thanking Trey and Gretchen for the invitation, for the organization of this wonderful meeting. So I'm very happy to be here and have the possibility to talk to you about some of the latest results we've obtained at Lens in Florence about the investigation of SUN fermions. And this is the outline of my talk. So after a brief introduction, I will tell you about some studies we have performed on multicolor physics of strongly interacting fermions. And then I will tell you about some new results about two-orbital magnetism. Okay, so let's start with a brief introduction. And we are working with two electron atoms. And two electron atoms are a particularly interesting class of atoms for atomic physics, since they can be used to merge two different worlds of atomic physics. On one side, one has the world of precision measurements, and we have heard this morning about the possibility of building optical clocks with 18 digits of precision. And on the other hand, ultra-cold two electron atoms such as ytterbium or strontium can be used to study the physics of quantum matter and quantum gases. Okay, so merging these two worlds together can open new avenues for quantum simulation and for quantum information processing. In this talk, I will mostly concentrate on the possibility of performing quantum simulation and looking at some interesting many-body physics with two electron atoms. So in particular, I will focus on ytterbium, which is the atom we are studying in Florence. And we have heard 2 days ago from Yoshiro Takahashi about very interesting possibilities offered by these atoms for quantum simulation. And I would like briefly to recall some of the main properties of these atoms. So ytterbium is a lanthanide element, but it has the same two-electron structure as alkaline earth atoms. And in particular, you have possibility to access singlet and triplet states. So you have efficient ways to laser cool these atoms, so working on dipole-allowed or intercombination transitions. And you have a lot of isotopes, and you can go down to quantum degeneracy, both for the bosons and for the fermions. And so you can produce BEC or Fermi gases. And in our experiment, we mostly focus on the Fermi gases, in particular of this isotope ytterbium-173. And I would like to remind you about two properties which are interesting in this respect. The first is the existence of metastable states. In particular, the lowest triplet state, which is connected to the ground state with an ultra-narrow clock transition. And on the other hand, these two states have another interesting property. So these are states with J equals 0, so with 0 electronic angular momentum. So the spin of the atoms come entirely from the nucleus, and you don't have any hyperfine interactions coupling the nucleus spin to the electronic degree of freedom. And this is pretty important in order to understand how these atoms interact one with the other. So let's consider ytterbium-173. It has a nucleus spin of 5½ So this means that you have 6 possible nuclear spin projection states. And so since these are nuclear spins, so the dipole magnetic moment is extremely low. So dipole-dipole interactions are completely suppressed, and so you are left only with two-body contact interactions, which are mediated by the electronic wave functions. And since you don't have any hyperfine coupling between the nuclear spin and the electrons, so this means that basically the way two atoms interact one with the other is independent on the nuclear spin projection. And so we can treat these nuclear spin states as if they were only colors for your fermions. So really, what is the spin projection does not matter. What matters is the number of possible internal states for your atoms. And it has been highlighted that this kind of system exhibits an SUN symmetry, where n is the number of states that you can access. And we have a good control of this nuclear spin degree of freedom, so we can image the nuclear spin composition with an optical Stern-Gerlach detection. So you can see here different clouds corresponding to different nuclear spin states. And we have also the possibility of manipulating the composition of a nuclear spin. And so by using optical pumping techniques, we can produce Fermi gas with 1 component, 2 components, all the way up to 6 components, so realizing different kind of symmetries in the system. Okay, so we have realized, we studied in the past, so in the last months, the physics of a fermionic gas in the presence of multiple internal states. So I will briefly recall some of the results we achieved. And these results have been recently published in this Nature Physics paper. Okay, so we are interested in studying the effect of interactions in a multi-component Fermi gas. And so since we don't have Feshbach resonances in this kind of atoms, we need to amplify the effect of interactions by using optical confinement. And in particular, we are interested in going to low dimensions, so in particular in one-dimensional setting, which can be produced by a two-dimensional optical lattice, which creates one-dimensional fermionic wires. And of course, 1D physics is very interesting because the effect of correlations between the particles is strongly enhanced by the low dimensionality. And so with this kind of system, we can realize systems of strongly repulsive fermions in 1D, and we can answer this question: how does the physics of strongly interacting fermions depends on the number of internal states? And so we have measured several properties of this system, for example, static properties, starting, for example, from a momentum distribution of this system. So what you can see here is the momentum distribution of spin polarized Fermi gas. So we can control the number of spin states, so we can now look at how this changes when, for example, you populate two different spin states, 3, 4, 5, or 6, and you can see clearly that you observe a broadening of momentum distribution. So in this kind of experiments, the number of particles per spin component is fixed. So this means that the Fermi momentum is the same for all the different combinations. And so what you see here is the population of larger momentum states, which is induced by the fact that you are building up correlations in your system. So I don't have the time to discuss this in detail, but I will be very happy to answer your questions at the end of the talk or after. But just like to give you some intuitive picture of this. So if you have a Fermi gas, so if you have n particles in a box, and you populate this box with n more fermions in different internal states, so if these two fermions are not interacting, nothing changes, and so you will have the same properties, for example, same momentum distribution for your system. Instead, if you have interactions, and so let's consider the case of a very strong repulsion, so let's say infinite repulsion, you will build up strong correlations in the system. So in particular, you will develop a sort of effective Pauli principle which forbids the occupancy of two fermions different internal states of the same position in space. And so in this kind of fermionized picture, so particles will be more localized in space, and so they will occupy larger momentum states. And in our experiment, we are exploring this kind of physics, and our experimental parameters are here in the strongly correlated regime in between these two limiting cases. Then we can study also dynamic properties of a system. For example, we can look at the low energy spectrum, which can be accessed via Bragg spectroscopy. And so what you see here, for example, is the excitation spectra at low momentum for a spin polarized Fermi gas. And as you increase the number of spin components in the system, you see the effect of interactions which shift this energy spectrum to higher energy, which means higher speed of sound for the excitations in your system. This for 2 components, and this for a 6-component Fermi gas. And now one can wonder whether this enhanced effect of interactions for a multi-component Fermi gas is just a quantitative effect, just a renormalization of interaction, or if there is something more happening. And we can answer this question by measuring a key property of quantum gases, which has been studied a lot since the beginning of the BC era. And this is the frequency of collective modes. For example, we can study the frequency of breathing oscillations, so which can be induced by quenching the strength of harmonic trap, which traps these fermionic wires, and looking at this breathing oscillation frequency, which is plotted here as a function of a number of spin components in the units of a trap frequency. And what you see is a redshift of this breathing frequency. In particular, for a spin polarized Fermi gas, you recover the value which is expected for one-dimensional fermions, one-dimensional non-interacting fermions. In the 2-component case, we observe a slower frequency of this breathing mode, and this is in very good agreement with some predictions which have been formulated by the Trento group. And this paper published almost 10 years ago, and we have a very good agreement. And by increasing the number of spin components, what we see is a lower frequency. And this is, again, in very good agreement with recent calculation performed by our co-workers Hu and Xia Liu from Swinburne University. And you see here a very good agreement between theory and experiment. And there is also a nice insight into what is happening when you have a Fermi system with many internal states. So what you see here is that the experimental data starts to approach asymptotically some kind of stationary value. And the same happens for the theoretical curves. And this stationary value is given by the breathing frequency you expect for one-dimensional spinless bosons. And this is a pretty general property of one-dimensional multi-component fermions, which has been first predicted by Nobel Prize winner Cheng-Ning Yang a few years ago. And by looking at the Bethe-Ansatz solution, exact solution of this system, so many properties of a system in the limit of an infinite number of spin components, of a fermionic system with an infinite number of spin components, approach the ones that are predicted for a spinless bosons. And this is, as far as we know, the first demonstration of this, let me call it bosonization, a kind of pretty improper way, bosonization of large spin fermions. Okay. Now, let's go to the second part of my talk, which contains more recent results about two-orbital magnetism. And these results are contained in this paper, which is about to be published in Physical Review Letters. And before explaining what we have done, I would like to mention that ytterbium is a nice atom to perform this investigation of multi-component Fermi gases. The reason is the following. So the SUN symmetry that I've described before has also an important consequence. The consequence is the following. If you prepare the system in a certain number of nuclear spin states, because of this SUN symmetry, this number is a constant of your experiment. So in other words, you don't have any spin-changing collisions that can mix the nuclear spin composition of your sample. In this sense, all mixtures that you can create in the experiment are collisionally stable. And in other words, if you take two fermions, one spin up and one spin down, and you consider the collision of these two fermions, there is no mechanism which can change the spin of these atoms, since these are nuclear spins which are not coupled to the electron wave function. And so the output channel, the output state, is identical to the initial state. And this happens whatever is the pair of colors for your fermions in the interaction. But now, remember that these are ytterbium atoms, two electron atoms, so we have access to an auxiliary degree of freedom. In addition to the nuclear spin state, we can access the electronic state. In particular, we have this stable state, the triplet P0, which is connected with an ultra-narrow clock transition to the ground state. And in the rest of my talk, I will call these states as G and E state. And by borrowing the technology which is being developed in the context of optical clocks, so in particular you need an ultra-stable laser which is locked onto a very high finesse resonator, you can access this transition and perform a coherent drive of this transition. This is what we can do, so we can have this is a typical spectrum of a clock transition in our experiment, which has a line width of a few tenths of a hertz, and you can also perform Rabi oscillations, which tells you that this process is coherent. So we can initialize a system in a coherent way. For example, we can produce a state like this, in which we have two fermions, one spin up and one spin down, one in the ground state, electronic ground state, one in the excited electronic state. So now you can see that the symmetry is broken. So because now these are different spins, but one of the atoms is excited. And so what you can have now is a spin-changing collision in which the two atoms, the ground atom and the excited atom, swap their spins. And this process is indeed a coherent process because it comes from fundamental laws of physics, so from symmetries of a problem. So let's consider the case of two fermions which are trapped in a trap. This trap is for us a site of a three-dimensional optical lattice. So these are identical fermions which share the same spatial wave function. Since these are identical fermions, you have to properly symmetrize the wave function. So you have two choices. You can choose either an electronic antisymmetric state and a nuclear spin symmetric state, or vice versa. So you have two possibilities, and it has been highlighted in this paper by Gorshkov et al. That these two states have, generally speaking, different interaction energies because of a different symmetry. You have different scattering lengths for this process. And so you might have an energy difference, which is the exchange energy for this system. So I can also rewrite these two states by dropping the subscripts 1 and 2, And you can see that these two states correspond to a situation in which the nuclear spin is highly entangled with electronic state. For example, here you can see that in these states, the G atom does not have a well-defined spin, and so the E atom. So if you start with a situation like this, in which you have a G atom spin down and E atom spin up, you expect to have a spin exchange interaction, in which locally you have this kind of effective interaction in which the two atoms in the two orbitals swap their spins. This is actually what we observe in the experiment, so we can resolve in real time this oscillation. And how do we do this? So first we have to prepare the state in a superposition of the two eigenstates. And we perform this by exciting the system on the clock transition at a finite magnetic field. So a finite magnetic field, it can be shown that the eigenstates of a system are superposition of a symmetric and antisymmetric state. And this can be done quite efficiently because remember that we have this very narrow transition, so we can spectrally resolve the interaction shift and only address the W-occupied sites. And also I'd like to mention that related work on this has been recently performed by the Fallani and Bloch group in Munich. So we can excite a finite magnetic field, this kind of a superposition, by exploiting the clock transition. And then we can quench the magnetic field in order to project the state onto a superposition of zero magnetic field eigenstates. And then, if just we wait some time, what we see is the following. So this superposition will pick up a phase factor because of different energies. So this is the exchange energy for the process. And so if we project the state now onto a measurement basis, which in our case is the magnetization of the ground state atoms, which can be measured with optical Stern-Gerlach technique, so you expect this magnetization to oscillate in time at this frequency difference. And actually, this is what we observe. So this is the magnetization of ground state atoms as a function of time, and you can clearly see that you can resolve this directly. For the first time, these spin exchange oscillations in which magnetization is swapped between the G and the E atoms. And actually, these oscillations are very long-lived. We have characterized their strength, and actually what comes out is that the frequency of this oscillation is pretty large. Actually, this is pretty close to the separation between bands in the lattice. So this is important because one needs to take care about how to analyze the data. So in particular, the usual Hubbard expressions for the interaction energy breaks down because you cannot use simply the single particle wave function. So you have to properly choose the wave function for your system. And this is because basically the scattering length in the antisymmetric channel turns out to be very large, so on the order of 3,000 Bohrs. And okay, so what is this useful for? So on one hand, we have demonstrated coherent control on the nuclear and electronic degrees of freedom, and we have seen a quite strong entanglement between these two degrees of freedom. So this interaction can be used, for example, for the development of new quantum information processing schemes. And on the other hand, so the fact that we can really resolve this spin exchange interaction, so this is a kind of magnetic interaction between different orbitals, it has been highlighted in this paper that this can be used to novel quantum simulation of strongly correlated systems. For example, for studying orbital magnetism, and also for studying Kondo models when you use state-dependent lattices to localize magnetic impurities. Of course, one expects these interactions to be SUN symmetric for the reasons I have told before. So one could check this, and I would like also to mention that related work has been performed by both the Fallani and Bloch group, which I've already mentioned, and also by Juni and Gila, with strontium atoms in a more clock kind of setting. And this SUN symmetry has been already verified to some extent, but now the possibility of really observing in time this long-lived spin exchange dynamics can be used also as a very precise quantitative test of this SUN symmetry. Okay, so I come to the conclusion, so I'd like to acknowledge the people who have worked on this experiment. In particular, I'd like to acknowledge the work made by Guido Pagano, who is the senior PhD student in the lab, who is about to finish and is also here present at ICAP. Then the other two PhD students of experiment, Marco Mancini and Giacomo Cappellini. And then more senior staff, so Jacopo Catani and Carlo Sias are both permanent researchers of the group, and of course, Massimo Inguscio. And also I'd like to acknowledge collaboration with people in Turin from the National Institute of Metrology who are working on a terbium clock experiment, and in addition, of course, of sharing the expertise in metrology and advanced lasers. There is a strong collaboration between the two groups, and this collaboration is also enforced by the fact that the labs in Turin and the labs at Lens are linked by an optical fiber link, which is dedicated for the transmission of ultra-stable laser signals from the two labs, and this can be used in the future for remote comparison, for example, between different terbium experiments in different places. Okay, come to the conclusion, and so again, I would like to thank the organizers for the organization of this wonderful meeting in atomic physics. And since this is the conference in atomic physics, I could not resist the temptation to a very small advertisement of a book that I've written together with Massimo on atomic physics, and it deals with two different aspects of atomic physics that we have heard a lot in this meeting. So both precise measurements and ultra-cold matter. So if you're interested, you can have a look at the Oxford stand in the hall. Okay, so this is my concluding slide, and with this I would like to thank all of you for your attention.
All right, we have time for questions now. Okay, Bill?
So I'm intrigued by the this concept of bosonization of large spin fermions. So you described, well, if you went to the infinite number of spin state limits for fermions, then they would look like bosons. Now it seems to me that if I had an infinite number of spin states, that all of the particles would be in different states, and I would think that rather than being bosons, those particles would be boltzons.
Yeah.
So what's the deal?
Yeah, this is a good comment. So I expect this, okay, first of all, this would happen at equals 0. At equals 0, and this would not affect all the properties of a system. So in a pretty similar way, I'd like to think in this way. So for example, when you talk about fermionization of bosons, when you're in 1D strongly repulsive, you know that the system does not behave in totally as a system of fermions. So for some respects, for example, for the properties which depends on the density, so for example, the breathing frequency does this job, this works. And it seems to work also in this case. So this is kind of a counterpart to the fermionization of strongly repulsive bosons. It does not have to be intended for all the properties. For the properties, if it depends on density, for example, the total energy or breathing frequencies, also the density itself, so this can hold.
Do you think they would behave like boltzons?
Oh, I mean, yeah, in some sense, yes. But for example, if you're at equals 0, expect, for example, the breathing frequency of thermal gas to be the same of a 1D Bose gas. So in some sense, yeah. Yeah, I agree with you. Okay, so it's okay. We cannot say, of course, that they behave in total as a system of bosons.
Are there any more questions? So if not, let's thank the speaker once again.